Hello everybody, welcome to Nonlinear Optics. As announced via Moodle, via email, we try a parallel session actually with Zoom, and I have the screen here in front of me. Unfortunately, almost nobody switches on the camera, so if you would do so, then I actually would have half the feeling of a classroom, or say a quarter of the feeling of a classroom. The idea is, of course, that you can give more immediate feedback, and nevertheless, you are not on YouTube, so that should work nicely. Ah, yeah, very nice. 3 students in the classroom here. So at some point, I'll buy a bigger screen here so that I have a more natural feeling. Okay, so I made several announcements via email, and just let me repeat a few. We were, so I was discussing a little bit my philosophy on a final. So what's going on? So if you are talking, if you're chatting to each other, then this is the same thing as if you chat in the classroom, right? So then I would need to switch off, well, my microphone, and then it makes no sense. So you have to behave as if you would sit in a classroom here in Zoom. So the Zoom classroom has should not talk too much. So there's a question. Yeah, please ask. Your microphone is on in YouTube and in the Zoom. Okay, so I switched it off in Zoom, but you could have also switched it off in Zoom yourself. Okay, so let's do it this way. Okay, so I hope everything is fine now. I talked a little bit about my philosophy in the final, and I hope everybody is fine with it. I hope you like the approach. The other thing that I discussed in my second email that I sent to you is about, well, what comes next in this course. Today we'll talk a little bit about symmetry properties, but then another major part in this nonlinear optics class is self-phase modulation. So it's a third order process, not a second order process as so far. And well, we'll talk about self-focusing, self-phase modulation, all these effects that are related with the intensity-dependent refractive index that we discussed earlier. And already at that place, I made the remark that this is an important class of phenomena. And we'll arrive eventually at another important law, another important equation, similarly important than the coupled wave equations, and this is the nonlinear Schrödinger equation. The nonlinear Schrödinger equation describes the propagation, the nonlinear propagation of short pulses, or of pulses in general, in a medium. So where all these effects, in particular self-phase modulation, also play a role. And well, as the starting point for nonlinear pulse propagation, we have, of course, linear pulse propagation. And as you might guess, if nonlinear pulse propagation is described by the nonlinear Schrödinger equation, then you might guess that linear pulse propagation is described by a Schrödinger equation. I won't have the time to derive all these concepts that you need in order to write down the Schrödinger equation for pulse propagation, for linear pulse propagation. But I prepared a LaTeX script, a nicely typed script on all that material, and the first part of that I provided, and I will also provide a YouTube link to that in the comments to this lecture, so that you can download this even if you are not part of this class and have no access to our Moodle channel that we have in addition. Okay, so, and I hope that I managed to write the other half of that chapter, later this week, so that I would provide it on the next weekend. Good. So I think with this we can really start with this lecture. What we finished last time was phase matching and a bunch of related phenomena like walk-off and so on and so forth. And today we'll start with something new. And the motivation for that, well, I could start with the coupled wave equation. For example. So if you look at the coupled wave equations, there we introduced this effective nonlinearity, and I made a few remarks when I wrote it down. I said that it has to do with the susceptibility, with the nonlinear susceptibility. So here you see the coupled wave equations for some frequency generation and for second harmonic generation. Well, one thing has been that we write the same nonlinear, effective nonlinearity in all of these three equations. And well, today I have to be a little bit, I have to explain a few backgrounds of that. I can only do this in a very, from a very high altitude, so to say. You will find much more details in the script if you're interested. The information I give today is just in order to, to know some of the caveats that one should know if one writes things like this. Yeah, so with this, let's start with the lecture in a more narrow sense. So we will talk about symmetry properties of the susceptibility tensor, and I want to start with some additional motivation. So let's write down the following. What I have to do is actually to write down the polarization as a function of the electric field, so this tensorial equation. So motivation. The nonlinear polarization. Oh, what's that? The nonlinear polarization for a three-wave process, which we take as, well, just as an example of nonlinear processes in general. This is given by as we have seen in the second chapter or so, I look at the polarization at the frequency omega L, and then I would write down this tensorial equation where we have the susceptibility tensor, second order susceptibility tensor, and now I should be specific about the frequencies. So I should also write down the frequency argument. Well, for brevity, we left that out often, but strictly speaking, it should be included. Yeah? So the idea here is that I have these two input waves, so to say, right? And if this would be some frequency generation, then, almost, then this is what we would get out. Yeah? So, and the nomenclature here is such that the sum of all three arguments sums up to 0, such that, well, such that frequency matching, that energy conservation is fulfilled. Yeah? So this is one part. And then, of course, what's still missing are the electric fields, now at frequency omega n, and the other component at frequency omega m. Yeah, so this would be the equation in full beauty, if you wish so, or you can also say in full ugliness, because what you see are a lot of components. The tensor itself, so the susceptibility tensor, has 27 complex components. 27, did I say? 27 complex components. But now, if you think back at the coupled wave equation, yeah, so here the coupled wave equation, then of course, what we mean with the first coupled wave equation would be, well, here we would have the susceptibility that as a polarization has omega 1, whereas here we would have another susceptibility tensor because we want to calculate the polarization at omega 2 and so on, right? So what you see is that if one wants to describe the interaction of three waves, then one has to know the susceptibility tensors at other frequencies also. Yeah? So let's write down that. Yeah? So it's not only 27 complex constants, but it's actually more. It is 12 times 27 components if you also take the negative frequencies. Yeah? So let's take a respective note. However, by far, this is not the full story. Yeah, let's write it down a little bit different. These 7 complex components are not sufficient. Rather, we saw that three waves are interacting. Yeah, and our simplification was a quite dramatic one. Yeah, so we reduce all these, well, 324 or so components. We reduce this basically to just a real number. Yeah? Yeah? Rather, we saw that three waves are interacting. I wanted to write in the coupled wave equations. For each of them, there would be a different chi2. Yeah? So now including all these one would need 324 complex, 324 tensor components to describe and this is just a second order process, yeah, to describe a second order process in the most general case. Yeah, but fortunately, there are symmetry arguments which we'll see reduce the number of tensor components quite drastically. Actually, we saw already one example with the most dramatic reduction, namely reduction to 0. Right? So we saw that we have a material, if we have a material that has inversion symmetry, then there's no second order effect, which means that the susceptibility tensor is equal to 0. So fortunately, there are symmetries which reduce the number of components drastically in general. Yeah, and the goal, or one of the goals of this lecture, is to explain how we come from, or how we go from the susceptibility tensor, how we arrive at this effective nonlinearity df. So we start out with, well, there are actually two classes of symmetries, I could say. So one class is geometric symmetries, namely the symmetries of the crystal itself. Right? So if you have a crystal that has, say, fourfold symmetry, then if you rotate this crystal by 90 degrees, it just looks the same, and therefore also the effect has to be the same. Yeah, so these are geometric symmetries. And on the other hand, we have the non-geometric symmetries that that originate from different reasons, and I will just briefly summarize them in the following. So that would be chapter 8.1. Non-geometric symmetries. And the most general one of these is the so-called intrinsic permutation symmetry, which just comes from, which can be traced back to fundamental properties of response functions. Yeah, so strictly speaking, susceptibilities are response functions. Yeah, so you have a cause, which is the electric field in our case most of the time, and you have an effect, which is the polarization. And then you can say, well, this function, this susceptibility, this mediates between cause and effect. And of course, this mediation function, this susceptibility has to obey certain fundamental properties. The most important is probably causality. So, which just means that an effect that you watch today cannot be caused by an electric field tomorrow, but just by an electric field today or yesterday and so on, right? And and this gives a certain structure for these response functions, and well, some of the consequences. So one of the consequences is intrinsic permutation symmetry. So let's write that down. In the script, you will find the derivation of that. So the most fundamental symmetry, the most fundamental one, is derived from basic properties of response functions. Yeah. And this is intrinsic, the so-called intrinsic permutation symmetry. What it says is the following. It says that if you look at this susceptibility, then you may flip here, you may interchange these two arguments, so these two frequencies, if you exchange the respective indices at the same time. Yeah? And it says that you can flip all the indices but the first one. Yeah? So this means, of course, for second order nonlinearities, that we just can flip these two. But if we would have third order nonlinearities, then we would have an additional argument, and then I could flip all three, but not the first one. Yeah? And once again, if you flip these two, then you also have to flip J and K. Yeah? So this is intrinsic permutation symmetry. So we just write it down. So we have Hij of minus F3, F2, and F1, that this is equal to I Kj, and then minus F3, F1, and F2. Yeah? So in principle, perhaps I should have mentioned that before. Yeah, so in principle, it would be sufficient to for Chi to note the two frequencies, because the third one must be there. But you see at this example why it's useful to include this, well, redundant frequency, because then you can write down the symmetry properties in a nicer way. Okay, so this was the first one. This was the first symmetry, here just given without any proof or so. The next one, which is similarly fundamental, is the fact that if you flip the sign of the frequency, then this corresponds to the complex conjugate of the susceptibility tensor. Yeah? And this property just comes from the fact that the fields that we are dealing with, also the polarization, are physical quantities and therefore are real numbers. Yeah? So similarly fundamental is that that Chi of minus F is equal to the complex conjugate of Chi of plus F. Yeah? This can be traced back to the requirement that fields are real. So next come symmetry properties that are less general. Namely, these symmetry properties only hold for special conditions. And the first one would be that if you have lossless media, well, strictly speaking, no medium is lossless, but some of them are approximately lossless. And then what I'm going to describe is perhaps not exactly fulfilled, but approximately fulfilled. So if we assume that we have lossless media, then we don't need the restriction that we had so far for intrinsic permutation symmetry. Remember, for intrinsic permutation symmetry, we said that you may permutate all frequencies but the first one. And of course, the same for the indices. Now if you have lossless media, then you can also flip the first with the second and the first with the third and so on. You can permutate as you wish, but you still need to flip at the same time the respective index. So, and this is called full permutation symmetry. So that would be the third point, full permutation symmetry. We have for lossless media, it can be shown that also the first argument, so the first frequency, and the first index may take part or may be permutated. May be, simultaneously, as usual. Simultaneously permutated. Yep, so just to be explicit, we could write that chi of ijk of minus f2, and then we have here f1 and f2 minus f1. That this is equal to, what's that? To chi jik, and then we would have f1 on the first position, and then minus f2, and without change, the third one, f2 minus f1. Yeah. And then there's a final one, namely Kleinman symmetry. And Kleinman symmetry basically says, do what you want. Yeah, so you can flip the indices without flipping the frequencies. And the precondition for that is that we would be far off resonance. Far off resonance means that the refractive index is not very dependent on frequency. Well, so in the extreme case, the entire susceptibility tensor is not very dependent on, virtually not dependent on frequency. And if this is the case, of course, you can do with the frequencies what you want, right? So in some sense, so presented like this, it's almost trivial. So this would be the last point in this subchapter, Kleinman symmetry. It's just one n. So far off resonance, media are more or less independent of frequency. And this means indices can be flipped or permutated is nicer. Permutated regardless of the frequency arguments. Good. I looked up who this man was, Kleinman, and finally found him. Like this here. So this is David Almond Kleinman. He was an important theorist in the early days of nonlinear optics. So here you see him on a photo where he's shown with a KDP crystal. It was the first, important nonlinear crystal that people used. I'm not quite sure whether whether his birth year is right. It could also be 1925. So it's difficult to find these persons. So this paper, for example, is quite a famous paper and still cited today, because the question is, of course, always whether these conditions for which Kleinman symmetry holds are fulfilled or not. And it's actually quite interesting to read just the first few sentences. Right? So here in the abstract, it basically says, in many cases, this would greatly reduce the number of independent constants. That's exactly what we are after, describing the effect. In particular, for quartz and KDP, there would be a single constant if Kleinman symmetry is fulfilled. And then this paper starts out, the recent observation by Frankenhill and Peters and Weinreich. And this is the paper on second harmonic generation. So this was actually, so if you think back about in the time, so 60 years ago or so, when the laser was invented, some people were saying that this is a tool that looks for a problem. And actually, nonlinear optics turned out to be the right problem for the laser. So it was Franken who realized this. After listening to a talk on lasers, he figured out what the fields are, and he figured out that this is not so far away from the atomic forces inside the material. And thus he just rented a Ruby laser and started out to do this experiment. There's a very nice story that I got from an article by Jeff Hecht, who kindly sent me this article yesterday. And I put it on the Moodle web page, so students, so you may want to just read a little bit about the history. And if you read this article, then you see that, that what it discusses, so these, first 20 years of nonlinear optics, that this is pretty much of what we do in this course. So now the second part of this chapter are crystal symmetries. So the reduction of the number of independent components of the susceptibility tensor due to symmetry arguments, due to the argument that I said, if you have a crystal that, again this example of fourfold symmetry, then if you rotate by 90 degrees, physics wouldn't make it, the physics is the same. Yeah? So symmetry properties due to crystal symmetry. That's 8.2. Symmetry properties due to crystal symmetry. I wanted to write here, well, I'll do it later. So 8.2, of course. Yeah. So the argument is the following. It's just what I said. Yeah? So we would transform the we would rotate our crystal, or we would apply the symmetry operation. It may not only be rotation, but also taking the mirror of the mirror lattice of the crystal, whatever it is. Yeah? So what it means that if we apply the symmetry operation to the susceptibility tensor, then the same thing should come out. And this gives a set of equations that can be used in order to determine, well, how the different components of the symmetry tensor, how they are connected. So crystal symmetry means that if a certain symmetry operation, I call it S, like symmetry, yeah, so with this double S kind of, that a certain symmetry operation, this can be inversion, or rotation, or mirror, or a combination of that. So if a certain symmetry operation is applied to a crystal or the respective chi, the lattice or the respective effect will be the same. Yeah, and now the question is, of course, how transforms a tensor, right? Everybody knows how a vector transforms. So we would apply, for example, a rotation matrix to that vector and get the rotated vector. If we have a matrix and we want to transform a matrix, yeah, so if you think back on mechanics, for example, so where you might have rotated the tensor for the motion of rigid bodies, Trägheits tensor, inertia tensor, then you know that you need to multiply the rotation vector from both sides, one of them transposed. If you have a third rank tensor, then it's more convenient to use this Einstein notation that we are using. So for third rank tensor, you have to apply this symmetry operation 3 times. So a third-rank tensor, and you can easily generalize this to higher order tensors. So if we have dijk, then it transforms like, so the transformed tensor d prime, and here the component ijk, that this is equal to the symmetry matrix. So this, then we have Jm and Kn, and here dLmn. Right, so this is the rotated or symmetry transformed tensor. And what we demand is that this primed tensor is the same as the original one. We demand, and this is the decisive sentence here, we demand that this is equal to the non-transformed tensor. And we do a first example here, namely once again inversion symmetry. And this means, of course, that the symmetry operation is, well, inversion, which means that we change the sign of all the components. So inversion symmetry means that this vector S, this matrix S is equal to to this inversion matrix, which would be -1, 0, 0, 0, -1, 0, 0, 0, -1. And you could also write this as -1 times the Kronecker symbol. And now we use this equation here. And well, what we want to find out is actually that all components of this tensor D are equal to 0. So according to, well, this equation here above, let's call it equation 1. According to 1, the tensor d prime ijk of the crystal after inversion must be the same as dijk without a prime, which is the tensor before inversion. And now we can write this down. dijk should be equal to d prime ijk, and this is given by -1 times -1 times -1 and the Kronecker symbol. So DILDJM delta Kn, and this is equal to -1 times dijk, right? And from this we get the dijk is equal to 0, right? So a result that we already had, but now derived here with an approach that you can generalize to other crystals. And I'll show you another example here just on PowerPoint slides. So here we are. So we look at crystal class 2, 2, 2, which means that we have 3 orthogonal axes around which we can rotate by 180 degrees without changing the crystal lattice. Yeah, so you can rotate around the x-axis, around the y-axis, and around the z-axis without changing the lattice. And the symmetry operations are the following. This you see here. Yeah, so here we rotate around the x-axis, therefore, well, the first index is not changed, but all the other ones are inverted. Same for the y-axis and the same for the z-axis. Yeah? And now we have 3 symmetry operations, and therefore there are 3 such conditions. Yeah? So the first one for the x-axis, then for the y-axis, and then for the z-axis. And now, as a first example, we just may want to apply, say, this operation here. We may want to apply it to the first component, yeah, so to D111, right? And this should be equal to D prime 111, which is given by, well, by the respective yeah, so which you can calculate using this, this matrix here. And when you do so, then you realize the same thing that we had before, namely that you have 3 times minus 1, right? So that D prime 111 should be equal to D111 to minus D11, and therefore this component is equal to 0, right? Now we try to generalize this a little bit more. So we write the general case here, right? So where we then we for rotation around the z-axis, yeah? And then we would have this equation because, well, we have only components on the diagonal. Yeah, so therefore I, j, j, and k, k here. And now you see, if we have an even number of minus 1s, then we get if we have an even number of minus 1, then we get, of course, plus 1, and we can't say anything about this component. But if we have an odd number of 1s, so 1 minus 1 or 3 minus 1s, then we see that dijk would be equal to 0. Yeah? So, or in other words, yeah, so this will lead here to plus 1 if there are 3 threes in this, well, a triple of indices, yeah, which is of course only true for 3, 3. It would also be plus 1 if there's just 1 3 there, right? And it would be minus 1 for all other cases. Yeah? So if there are 0 or 2 threes in this triple. Yeah? And the immediate consequence is that the respective tensor components would be equal to 0. So what we now do is that we write down all these triples, and this is what I did here, right? And we can now immediately say that, well, if there is no or 3 or 2 threes in one of these triples, then we can cross them out, right? And I did this, and you see, well, in 111 there's no 3, so therefore it's gone. You also see the last one, there are actually 2 threes, so it's also crossed out, whereas for the other cases, well, there's just 1 3, and therefore it survives. Yeah? And now we do the same thing for the other components, for the other symmetry operations, namely for the x-axis, right? So there we would say if there are two threes, or if there's two ones or 0 ones, then we also have to cross it out. Yeah? So if there are 2 or 0 indices equal to 1, then we have to delete it, right? And I did this, and you see, right? So first example here, we have 2 zeros, 2 ones, and the same thing here, and well, yeah. So I did it this way, and we can do the same thing with the y-axis, where we have to cross out all triples that contain 0 or 2 indices of value 2, right? And this is done here. And so you see what survives. Yeah? So we have just 2 components in the first layer of the tensor, 2 components in the second layer, and 2 components in the third layer. So we have just 6 components that are not equal to 0. But then it can still be that some of these components are actually equal. Yeah? So perhaps due to Kleinman symmetry or whatsoever. Yeah. So here, for example, in the case Kleinman symmetry holds, yeah, so this means that the crystal has no dispersion, yeah, throughout the spectrum that's of interest. Then this means that all indices can be permuted, and then the crystal class 222 would have just one independent component. So 6 non-zero components, but all of them are equal. Yeah, and people did this, of course, and you may also wish to do one or the other example. You can use a program like Mathematica in order to automate that. And then you find for the crystal classes, well, here we have the uniaxial crystal classes, so particularly relevant for nonlinear optics. Then here the biaxial crystal classes, and here the isotropic crystal classes. And you see that in the isotropic crystal class, there's only one, two classes that have a non-vanishing components here. One thing I forgot to mention here. What we use here is again this contracted notation. Yeah, so you remember, and I'll come back to this point in a minute or so after the break. You see, we use here contracted notation, so this kind of trick in order to make a 2-dimensional matrix out of a 3-dimensional tensor. And so perhaps I should explain a few more things. Yeah, so if you have this gray dot, then it means that the component is equal to 0. You might have guessed that already. If they are connected, then this means that that these components are equal. You see that in this case they are dashed, so this connection is dashed, which means that they are equal only if Kleinman symmetry holds, as I mentioned already. If we have open symbols here and neighbors which are connected to closed symbols, then this means that both components have opposite sign. And then there's a final thing. We have also square dots here, which means that that they are equal to 0 if Kleinman symmetry holds. Yeah? So far for this kind of symmetry properties. After the break, so we'll do 5 minutes of break or so. After the break, we look at how to derive the effective nonlinearity for a certain example. So see you in a few minutes. So let's continue. We want to see how the effective nonlinearity is calculated. We do it for one example, and then you would just look up the equations in a textbook. So I need to start with repeating the contraction of indices. I just announced that. We did this in chapter 1 when discussing the electro-optic effect, but now I also have to explain on how the electric field is actually rearranged in order to use this trick of writing a three-dimensional tensor in a two-dimensional matrix, in a 3.6 matrix. You certainly remember that we had, so we start with this equation, and then what we said is that if we have a symmetric tensor, right, then we can write. Well, we discussed it. So the easiest thing is to start with a symmetric matrix. Then you have 6 independent components, and what we do is that we write if x and if y and k is equal to 1, 2 for the second element on the diagonal, and 3 for the third element on the diagonal. So this would be k equals to 3. And now the question is what happens to the other one. So if we have y and z, then we give it the index 4, and so on and so forth, right? And just that you are able to remember it, if you replace, so if you take the sum of this index, so now my pointer is gone. I charged it before the lecture. That's unfortunate. So that it's gone when I need it most. So the trick to remember this is that if you sum the 2 indices that you replace together with the replacement, so now I have just a pointer. So if you sum, for example, in this case, there we would have y, so this is index 2, and z, this is index 3. 2 plus 3 plus 4 is 9. The same thing here. Here you would have 1 plus 3 is 4, plus 5 is also 9. And this here, that's really unfortunate. So maybe it's just the computer. Okay, I think we make another break. And I try to fix this. I hate it. sorry for that. So let's see whether it works. Okay, yeah, so it was the computer, not the remote. Yeah, so once again, contracted notation. Yeah? I just explained on how to determine these numbers here. So now, if we want to also write the field in contracted notation, then we have to do it in the following form. So it's actually defined here, right? And well, I don't derive it here, but you can just check that this fulfills actually the relations that you would get if you would use, well, if you would write down this here. Where is it? Yeah, so if you would write down this here, then you would get the same thing as if you use this form of equation, right? And the polarization you would get by matrix multiplication, so 2 times, and then you would multiply, would take the scalar product of this row here with this column, right? And then the second one in order to get py and so on and so forth, right? And of course, for the second harmonic generation where 2 frequencies are equal, it simplifies a little bit because xy and yx would be the same thing there. So this was just to repeat contracted notation because we need it now. And what we do is that we derive the effective nonlinearity for a certain configuration in crystalline quartz. And the geometry that we assume is the following. We have the optical axis here, and we have a beam of light with wave vector k prime and k double prime. They are distinguished by their polarization, as you'll see in a second. And this beam is has an angle of theta with respect to the optical axis. Yeah. And now we have 2 polarizations here. So we have 2 beams with two different polarization. One is K prime, as I said, and to K prime corresponds the field E prime, and to K double prime we have the field E double prime. And if you look at the situation that we have here, then you recognize that E double prime is the ordinary beam because it's perpendicular on the optical axis, yeah, and therefore doesn't depend on the angle theta. Right, so the refractive index would be independent. So it would, so independent of the angle theta, E double prime is perpendicular on the optical axis. And this is of course not the case for E prime, and therefore E prime would be the extraordinary beam. So now we look at this figure 5. We look head-on the optical axis and this plane. So you see the optical axis here. So we just see the dot coming out of the, so this, this line coming out of the drawing plane. And you also see the cross-section of this plane. So this green line here, this is what you would see from this plane here, which contains E double prime and K, right? If you look head on this, then you just see this here. Yeah? And I also indicated here this wave vector that comes out inclined, going here up, but out of the drawing plane. Okay, so what we also, what I also draw here is the rest of the coordinate system, right? So here the x-axis, so we have the z-axis going in this direction, and now here we have also the x-axis and the y-axis. What we assume, of course, is that the coordinate system is aligned to to the unit cell of the to the lattice of the crystal. Right? So therefore, in general, we have this angle phi here. Okay, quartz belongs to the symmetry class 3-2. Right? So there's a threefold axis and a twofold axis. And then we just can look up on the table that we have shown before that this symmetry tensor in reduced notation has this form here. Right? And now we look at a special case, namely, do I write this already here? Okay, we look here at, so we use this definition that we introduced just, right? So we have F1, F2, F3, and F4, and F5, and F6, right? And then we write down, together with this matrix here, we write down what the polarization is, P1, P2, and P3. So for P3, you immediately get 0, of course, right? So if you multiply this with this column vector F, then you immediately find 0, but also the other ones are, well, so they're just 3 components and 2 components. So the second line has just 2 components. Okay, so what we now need are the components of E prime and E double prime in the coordinate system of the crystal. Yes, we are in the coordinate system of the, so this is written in the coordinate system of the crystal here, and therefore we also need to find E prime and E double prime in the coordinate system of the crystal. Well, that's easy. It's just a little bit of trigonometry. If we start here with E double prime, then it's clear that it has no z component. It's perpendicular on the optical axis. You see immediately there's no z component. So we still look head-on of this on this. So same perspective than in figure 6. And then we have here E double prime is perpendicular here on the optical axis, which just comes out of the plane here. And then we can find EY and EZ very easily, right? So minus, so in this case here, minus EX double prime, this is equal to the length of this vector times the sinus of phi. And the same for the y component. Yeah? Well, for E prime, things are slightly more complicated. Yeah, so in the drawing, so in this plane here, what we see from this vector is the cosine of that vector. Right? So this projection here on, so this here would be the z component. Yeah? And then you can do the same thing. So E3 is easy. This is just the sine of this angle phi. And the others are then the cosine, but of course of just the component with, of this component here, E3. Right? And just to summarize everything, what we get are these, so E prime or three components here, and E double prime, or these components. And this we plug in into this equation 13, right? So we had these components here, and now we plug in all these expressions. And as you expect, it looks ugly, right? A lot of terms. Right? So nothing has happened. I just replaced this here. Right? Just stupidly substituted E1 prime. Right? So and you see this expression here, and you see E1 double prime. Right? So minus sign is also here, and then E double prime sinus of phi, and so on and so forth. Right? Well, then things can be simplified a little bit in some cases, namely that the cosine squared of phi minus the sine squared of phi, that this is equal to cosine of 2 phi. Yeah, so some trigonometry can be done. Well, actually also here I did some trigonometry. So you see this here. And this then means, so these are, this is then the result here so far. But now, so at this stage we are in the coordinate system of the crystal. Now we want to go back into the coordinate system in the lab, so to say, in the coordinate system of the wave vector and the optical axis. And so we define the polarization that is so that is parallel and perpendicular, say to E prime. So you can do the same thing for E double prime, and you would get other components. So now it depends on whether your second harmonic is the extraordinary beam or the ordinary beam. So whether you have type 1 or type 2 phase matching. But I do this example just for the nonlinear. So I pretend that I'm interested in the situation where the nonlinear polarization is parallel to E prime, so to the extraordinary beam. And then with the same reasoning than before, we find that the polarization perpendicular to E prime is given by this expression, and the polarization parallel to this, to E prime, is given by this expression here. So 16a and 16b. And then you can write down, so we just substitute this equation, these equations here. We just substitute them in, say, this equation. And then we get this expression here. So we have now the polarization being proportional to E prime and E double prime. Well, and this proportionality factor then by definition is the effective nonlinearity. And the same thing here for P parallel. just a little bit, more complicated, this expression, but this would be the effective nonlinearity in direction parallel to E prime. Yeah? And this you can also do, of course, for E double prime. And you can do it for all other crystal classes, and of course this is not fun to do. But people did it. So this so these are a few pages that I copied from the Zernike Mitwinder book. Well, this is actually the son of the famous Zernike. Yeah? So Fritz Zernike, the Nobel Prize winner for phase contrast microscopy, for example. This is not him. Yeah? So the book was originally published in 1972, and the old Zernike died in 1966. Here you find these expressions for all situations. Type 1 and type 2 phase matching, but also whether Kleinman symmetry holds or whether it doesn't hold. So here it's for the situation where it's valid, and I think the other one is where it's not valid. So Kleinman symmetry does not hold here. Yeah, so this is how we get the effective nonlinearity, and that's actually pretty much everything I wanted to explain today. If I would have done this just by writing everything down on the iPad, it would have taken me certainly 2 lectures or so. And today it was actually less than kind of 1 lecture. So we were a little bit too fast, but I think nobody would object to that. It's a lot of material anyway, but it's of course, there's of course not too much physics in it. Yeah? Of course, symmetries are always beautiful, and I kind of like to see how the number of independent components are reduced to a small number if one applies the symmetry operation. So I like this kind of physics. But of course, it has little to do with nonlinear optics per se. But you need to know, of course, what you're talking about if you look up, or if you see an effective nonlinearity quoted somewhere in the literature, you need to know where it comes from. And I think this I was able to explain today. In the next lecture, as I announced at the beginning of this lecture already, we will have another focus. We'll turn to third order process, in particular to the intensity-dependent refractive index, to the nonlinear refractive index, and we'll see all the some of the phenomena that are typical for that, and actually I introduced the two major ones already, namely the fact that self-focusing may occur, giving rise to things like filaments, and the other is that you can produce a lot of new colors just from just by shining in a short pulse into some material, because the short pulse changes the refractive index, which changes the phase in a time-dependent manner, and this is equivalent to saying that new colors are produced. And so these effects due to the nonlinear refractive index, in particular, if you look at it in a time-dependent way, this results in particularly colorful phenomena, and to all the important physics concerning nonlinear pulse propagation. Yeah? And if you just look at, say, at a titanium sapphire laser, then such a laser, such a femtosecond laser, relies in a very fundamental way on this kind of physics. A titanium sapphire femtosecond laser would never work if this phenomenon of cell phase modulation would not exist. So you see, it's a really important part of nonlinear optics, and the equation that governs that is, once again, the nonlinear Schrödinger equation. Has nothing to do with quantum mechanics, by the way. Yeah? So it's just called Schrödinger equation because it has this structure of a partial differential equation where on the one side you have a first derivative with respect to, say, the spatial coordinate, and on the other side of the equation sign you have the second derivative with respect to time, or vice versa. And when you have a partial differential equation of this type, then we call it a Schrödinger equation because it's so prominent in quantum mechanics. But this kind of equation also plays a huge role in other fields of physics, in particular of optics. And where the Schrödinger equation is a linear equation, the nonlinear Schrödinger equation, as the name says, is a nonlinear equation, and just the name nonlinear Schrödinger equation already proves that it has nothing to do with quantum mechanics, because in quantum mechanics, in quantum mechanics we have the superposition principle. This must be a linear Schrödinger equation. So there's a quote. Some of the famous pioneers of quantum mechanics said that whoever speaks of nonlinearity in quantum mechanics will be hanged on the apple trees in Niels Bohr's garden. So I think now it's clear nonlinear Schrödinger equation has nothing to do with quantum mechanics, but gives rise to very interesting effects in some fields of optics. The culmination of that are actually the creation of solitons. With this, I thank you for your attention and see you next Monday or tonight for another Zoom meeting. If you have some questions, you're welcome to ask them.